this section will be a little bit of a change of pace. So we've been looking at rational expressions. We learned how to multiply them, divide them, reduce them before that, and then add them and subtract them, even when they have unlike denominators. So we've kind of learned all we can about what to do with rational expressions, how to combine them in all different ways. So this section's kind of a change of pace. I guess it's saying, what if you have a rational expression within a rational expression? So kind of like a fraction within a fraction, you know? And you can kind of see a few examples here of a complex rational expression. So this one here I'm highlighting, it looks like it's a fraction over a fraction. So it's like the large numerator here is its own fraction, and then the large denominator is its own fraction. So it's kind of like a fraction as the numerator and a fraction as the denominator. And then the second example here, it's even more complicated because it's one big fraction where there's a fraction bar right down the middle, but there are fractions within the fraction. The numerator contains two fractions adding together. The denominator contains two fractions adding together. So you can see probably why they call it a complex rational expression. It's very complex. It's not just a normal rational expression should just be one fraction, kind of with variables and numbers in it. But if there are fractions within fractions, that's when we call it a complex rational expression. Okay, so this section of the book is all about how to simplify these. There are ways to make complex rational expressions simpler by making them just regular rational expressions, like we've seen in previous sections. And there are two methods on how to do it, so we'll learn both. I know it seems usually when there's two methods on how to do something, it just kind of confuses things. But this way, then you can kind of tell which one you like better, and then you can I would just say, kind of follow along and see which one you like better, and then just stick with one. Because I think if you try to memorize both, it's easy to mix them up, and then you won't remember which method's which, and you'll try to do both at the same time, and that won't work out. Alright, so let's just try reading over method 1 here. I'd say method 1, just the good thing about it is it's kind of what you would think to do. It's kind of a natural method, what you would think to do. Yeah, like you might guess this method. So it's kind of easier to remember. Easier to remember. So if you kind of feel like you have not a bad memory, well maybe a bad memory, but also you have so much in your mind that you're like, man, for the next exam there's already so much to remember. I'm going to try to do this method because it's the least to remember and it's the easiest to remember. I think the second method we'll see after these three examples here, it's harder to remember. You know, it's not very natural. You wouldn't think to do it probably, but it's faster. So you kind of have to decide, do you rather pick a method that's easy to remember, that takes a little longer, or a method that takes a little less time, but it's harder to remember. So it's up to you. And like I said, I would decide kind of as you try these problems and try the problems in the homework. Try a few one way, try a few the other way, and then you probably decide which one you like better. Alright, so method 1, like it says in the title, it uses division to simplify complex rational expressions. So pretty much what it does is it takes advantage of the fact that we know that any fraction can be thought of as a division problem. Like in this top example we have way up here, the fraction over a fraction, you can think of it as the top fraction divided by the bottom fraction instead of the top fraction over the bottom fraction. So what we're going to do is rewrite it as a division problem instead. So okay, step 1, but this first step, like if it's not one whole fraction, like the example we were just kind of talking about, that's just one fraction over one fraction. But what if it's more complicated, like example 1 part A here? You have two fractions in the numerator, two fractions in the denominator. Before you try to convert this to a division problem, you first have to combine any fractions that are within the numerator, combine any fractions that are within the denominator. So we'll do that first. Step 1 says you want to add or subtract as needed to get a single rational expression in the numerator. So pretty much they mean get a common denominator there between, in the numerator you got 2/5 minus 1/10. So I want to combine those into one fraction by adding or subtracting them. So I'll do that first. Let's see. Between their denominators, 5 and 10, the common denominator would be 10. I'll have to multiply the numerator by 2 and the denominator by 2. And then I think that should do it. Okay, let me see. And usually, excuse me, I usually kind of keep going with just the numerator here, like that'll make that 4 over 10 minus the 1 over 10 that was there. I'm going to leave an empty space down here for the, whatever happens with the denominator. I'm just going to kind of keep it the same for now though. Okay, now that those two fractions, the 4/10 and the 1/10, have the same denominator, now I'm free to actually subtract them. That's 4/10 minus 1/10, that's 3/10. Alright, so whatever happens in this problem, I know that the numerator simplifies to just 3/10. Now let's try, step 2 says, you want to do the exact same thing in the denominator. So down here we got 7 over 20 minus 4 over 15. I want to find a common denominator, let's see, between 20 and 15, I think their common denominator is 60. That one was a little trickier, the LCD is 60 between those guys. So that means for the first fraction, the 7 over 20, I asked myself, okay, 20 times what is 60? That would be 3. So I'll multiply that guy by 3 over 3. And then how about the second fraction? 15 times what is 60? That would be 4. So I'll multiply that guy by 4 over 4. And that'll do it. Alright, let me see. Now I'm going to rewrite what those new fractions are down here below the previous fractions. So 7 times 3, that's 21 over 20 times, 20 times 3 is 60. And then the same thing with the other fraction, we have 4 times 4, that's 16, and then 15 times 4 is 60. Alright, now that those have the same denominator, I'm actually able to subtract them. 21 minus 16 is 5 over 60, and actually, you know what, that reduces, so I think I'm going to take an extra step and reduce that. 3/10 on the top does not reduce, but 5 over 60 reduces to 1 over 12, I believe. 12 times 5 is 60. Yeah, so we kind of reduce that guy. 5 goes into 60 12 times. Okay, so we've done step 1 and step 2. That wasn't too painful, I don't think. Yeah, I was like, that was step 1 there, step 2 there. Now we're about to start step 3. Step 3 says you want to rewrite this as a division problem, because this really means you're taking the numerator and dividing it by the denominator. So it's 3/10 divided by 1/12. That's a different way to think of it. Instead of 3/10 as a numerator over a fraction with 1/12 as the denominator. And now that it's a division problem, I think I know what to do. It's like we said before, you flip the second one upside down, the reciprocal of the second fraction would be 12 over 1, and then you multiply. But I think before I multiply, like we've seen before in previous sections, with these rational expressions, you're going to want to, I guess, not just multiply, but reduce if you can. It's not much of a reduction, but I do see that 2 goes into both of these. 2 goes into 10 5 times, 2 goes into 12 6 times. And now that I've reduced as much as I can, I'm going to multiply across. In the numerator we have 3 times 6, 6, that's 18, and the denominator 5 times 1 is 5. And that's as good as that one gets. That cannot reduce anymore, so you must have done something right. So it's definitely, I think, pretty clear that these things simplify quite a bit, because look how complicated it started out. And all it really was 18/5 in disguise. It just looked complicated. So these are probably worth actually simplifying like we've been doing. Alright, so I think that was good. Let's try that on part B. It's going to be a little more complicated in part B because there are actually variables, so it's going to be a little harder, but at least by now we have the idea because we've seen part A with the numbers. Alright, so we have to go back to the beginning. Step 1 says you want to add or subtract as needed to get a single rational expression in the numerator. But notice that this numerator is already one rational expression. So really step 1 is already done for us. We can skip it. Now I'm going to move on to step 2. Step 2 says you want to add or subtract as needed to get a single rational expression in the denominator. Okay, that's actually something I'd have to do because I have 2 separate fractions there. So first thing I'm going to do is think about what's the LCD of the denominator. Well, looking at their denominators, there's a t and a t squared. Now remember, in your LCD, when we calculate the LCD, you want to make sure you have any factor, which either of them have is a t, to some power, but you want to have that factor the most number of times you see it. So since one denominator has 2 t's and the other one has 1, I want to take the most I see, which is 2. Alright, now that I know what the LCD is, now I can see, for the first fraction, what would I need to multiply it by to kind of force it to have that denominator. Well, the first fraction already has that denominator, so I don't need to do anything to it. It's really the second one I need to work on. So if I look at the denominator of the second one, his denominator is a t, so I ask myself, t times what would make that LCD t squared? That'd be another t, but I have to multiply numerator and denominator by the same thing. So that have to be a t over t. Alright, now I'm going to rewrite this. I'm going to keep the numerator as it is because we already said we could skip step 1. The numerator is already one fraction. The denominator now, like we said, we're keeping the left fraction the same, but the right fraction, now that we've multiplied it by t over t, it's going to become minus 5 times t is 5t, and then in the denominator, t times t is t squared. Okay, I think that looks good. Now I'm able to subtract those guys, and the numerator here is just kind of following along. 10 over t. In the denominator, if I combine the numerators, I have 2 minus 5t. Those aren't like terms, but at least I can write them as, over one denominator, so it's just one big fraction. And that's really all I can do for step 1 and step 2. Those are done. Now step 3, it said you want to basically rewrite this as a division problem. So it's the big numerator, or the fraction in the numerator, 10 over t, divided by the denominator, 2 minus 5t over t squared. Because again, remember that any fraction can be thought of as a division problem, if it helps. A lot of times in a fraction, it doesn't really help to think of it as a division problem, but in this one, it happens to. So I'm rewriting that guy as a division problem, and then I remember, how do I divide two fractions? I take the second one, you gotta flip it upside down to make it the reciprocal, and then multiply it by the first one. The first one's staying the same, division changes to multiplication, and now I have t squared over 2 minus 5t. Okay, and at this point, now that it's multiplication, I don't want to quite multiply across yet. I want to see if it reduces. So really what we're supposed to do is factor everything we can, because remember we said you can't reduce until you factor. But looking at the numerator of the first one, it's a 10. You can't really factor that, that's just one term. And then the t in the denominator, you can't really factor that either. T squared in the numerator there, that's not much you can do. And then the 2 minus 5t, the only hope I'd have, since that's a binomial, is maybe they have a common factor, but they don't. Or maybe it's a difference of squares or difference of cubes, but it's not. So really, nothing factors. I'm just going to see if I can cancel anything right now. I think the only thing I can cancel is the t here can cancel with one of these t's. So leaving it as 1t. So this t is gone because it canceled, but there's 1t left in the numerator. That's really all I can cancel. And don't make sure you're not tempted to just cancel like this 2 and this 10. If it was just a 2 in the denominator without the 5t, then it would reduce, but you're thinking of 2 minus 5t as one entire factor. So if it had any hope of canceling with something, you'd have to see 2 minus 5t, that exact whole thing, somewhere else. You can't cancel a part of it. Alright, now all that's left is to multiply across. In the numerator we have 10 times t. Since one of the t's cancels, there's only one left, so 10 times t would be 10t. In the denominator, this t is gone because I've canceled it. Really all that's left is the other denominator, 2 minus 5t. And that one, it seems like I can reduce because I have a 10 on the top, a 2 on the bottom. Those seem like they reduce, or the 10 and the 5. But keep in mind, 2 minus 5t, that's all part of one factor. You cannot cancel one part of it with the numerator. That's as good as it gets right there, unfortunately. Alright. So it's kind of a tedious process, it takes a little while, but like I said, it's almost what you would think to do, I guess. If you just if no one told you how to do these problems and you had to stare at it for a while and try to figure it out, this is probably what you would guess to do. That's why I kind of like this method. It's more natural than the coming method that we'll see. But the coming method we'll see is faster, so that's the advantage. Alright, but let's try this one more here. It's 1 minus 1 over x. That whole thing divided by 1 minus 1 over x squared. Okay, and one thing to point out is you can't cancel right now. Cancel. Remember, really, you know we said you have to factor before you cancel? The reason for that is you can only cancel when everything in the numerator looks like it's multiplied together. Say, there's a bunch of stuff multiplied together, this times this, and then in the denominator, same kind of thing, this times this. So you're only able to cancel when you see the product of a bunch of things. Something times something times something, that's when you can cancel, like whatever, if there's like terms. But as we have it now, we don't have the product of things in the numerator. It's 1 minus 1 over x. That's the difference. So yeah, we can't have any hope of canceling until everything looks like it's multiplied together in the numerator and the denominator. That's definitely not what's going on here. And this 1 over x cannot cancel with this 1 over x squared. Nothing can cancel yet. So really don't try to cancel until the very end. It's not going to work. It's tempting, but it's not right. So our first step was you're trying to make the numerator into just one fraction. So what I'd like to do is take this 1 and this 1 over x and try to write them as one fraction. But the only way I can do that is if I put this 1 over 1. Because it has to be a fraction minus a fraction. I can't subtract a fraction from a whole number. But if I write it as 1 over 1, then I'm going to think about, okay, what's the LCD between those guys? Well, at least common denominator between a 1 and an x, of course, is x. I'm looking at those guys and I say, alright, I'd like to see denominators of x. Well, for the first fraction, that would mean I'd have to multiply it top and bottom by x. That way it's, 1 times x over 1 times x. And let me see, I'm going to write down what happens to that guy. That would be 1 times x is x, 1 times x is x. Alright, that's the left fraction in the numerator minus, I look at the second fraction and I notice it has exactly the denominator I want. I want the denominator to be x. So I'm really just going to copy that guy down as is, 1 over x. Because your only goal is to get a common denominator. There's no need to, you don't have to multiply both of them by something, as long as they end up with the common denominator. Alright, now I have to do something similar in the denominator. That was step 1. Now in this big denominator here, I have 1 minus 1 over x squared. I have to do something similar if I want to combine those into one fraction. Put the 1 over 1, and then I have to see, for those guys, what's their LCD? Between 1 and x squared, of course the LCD is x squared. Pretty much every time you have 1 and something else, the least common denominator is going to be that something else. Alright, so I think, what would I have to multiply that 1 over 1 by so that it has a denominator of x squared like I want? Well, I guess x squared, huh? X squared top and bottom. It's starting to look a little messy, huh? Oh well, and then let me move that guy down here. So it's 1 times x squared, that's x squared, over another 1 times x squared, which is x squared. The second fraction, though, you have 1 over x squared. It already has the exact denominator I want, so there's really no need to do anything to it. I'm just going to copy it down the same way. Okay, now I'm going to combine those numerators. Now that they have the same denominator, even though the numerators aren't like terms, x minus 1, at least I can write them together over one fraction, over one denominator. And that's all over a big fraction of, the same thing in the denominator there, you have x squared minus 1 in the numerator. They can't really combine, they're not like terms, but at least you can write it as one single fraction. Alright, so we did kind of step 1 and step 2 together at the same time, combining the two fractions in the numerator into one fraction, and then the two fractions in the denominator into one fraction. Now we're moving on to step 3, which is, I feel like at this point you're doing, you feel a lot better, because all it is a division problem now, and that was a couple sections back. So I'm going to rewrite this guy. The big numerator is x minus 1 over x. And we're dividing by, think of the big fraction bar as a division sign. And then the denominator there was x squared minus 1 over x squared. There we go. Alright, at this point I always feel like I'm kind of home free. Because it's kind of familiar territory at this point. This is something we learned a couple sections back, so I'm not as nervous as I would be otherwise. Alright, so the first thing we have to do is change this guy to a multiplication problem. I'm switching division to multiplication as long as I flip the second fraction upside down to make it the reciprocal. If I flip it upside down, now x squared is on the top and x squared minus 1 is on the bottom. Alright, before, like in the previous example, before I multiply across, I want to see if any of these numerators or denominators factor. And then I'll reduce, if I can. Alright, so I think the only one that factors is this denominator here. So everybody else is staying the same since they're not able to factor. X minus 1 is too simple. It's a binomial, but it's not a difference of squares or a difference of cubes or a sum of cubes. And then the denominator of that guy, x, that's only one term. There's nothing you could do with that. Same thing with the x squared here. But the right fraction's denominator, x squared minus 1, that's actually a difference of squares. So if I factor that guy, it'll be x minus 1, x plus 1. And now that I've factored it, I see that one of those factors cancels there, so I'm going to take that x minus 1 and cancel it with this x minus 1. Anything else cancel? Yes. Across the other diagonal, this x cancels with one of these x's to leave 1. So what's left now? In the numerator, the x minus 1 is gone. One of those x's is gone. There's only one x left in the numerator. In the denominator, you have x canceled, x minus 1 canceled. Only the x plus 1 is left. And that would be it. That's our answer. And I'd be I see people there all the time. They're tempted to cancel those x's. But remember, the x in the denominator is part of a factor, x minus 1. It's a package deal. So you couldn't cancel a part of it. You'd have to see that entire x plus 1 in the numerator in order to try to cancel it. So that's it. I feel like that one really simplified quite a bit. That was nice. It started out really complicated, but it kind of became nice and simple. Alright, so now I think we probably get the hang of the first method. It's kind of tedious, you're trying to combine little fractions. Once you combine the little fractions, you can think of the big fraction as division, and then kind of finish the problem like we've seen before. We've seen dividing rational expressions before, so that's nothing new. I think this method you're going to like. Once you kind of get the hang of it, you're really going to like it because it's fast and it's almost kind of, I don't know, almost like magic. It works so nice. The only downside is I'd be worried if I had a bad memory, which I kind of do. When I get to the exam, I might forget how to do this one because it's not natural. You wouldn't think to do it. You'd have to just kind of memorize it without thinking, oh, this is normal. This is what I would guess to do. So it's up to you. If you feel like you have a good memory and you don't mind having to memorize something new that's not really natural, this is a faster method and it's kind of more fun in a way too. But if you think, man, I already have enough to memorize, I'm going to just use method 1 because it's easier to remember, then that's fine too. Those problems didn't take too long. But yeah, just to compare, let's try this method 2. So what we're going to do, like it says in the title, we're using multiplication by the LCD to simplify a complex rational expression. Alright, so first thing we're going to do, and we might as well follow along with these steps when we're looking at example 1 part A here. So first thing we're supposed to do, it says calculate the least common denominator of all the rational expressions within the complex rational expression. Okay, step 1, so basically they're saying look at all the little denominators. So like in example A, you have a denominator of 2 here, 4 there, 6 here, 8 there. So really the first thing you want to do is say, what's the LCD of all those little denominators, 2, 4, 6, and 8? So let's see, that's kind of a tough one actually. What would it be? I think 24 would be the one. At first I was thinking 12, but 8 can't divide into 12, right? So 24, I think that's the smallest number that all those divide into, basically. That's the easy way to think of it. What's the smallest number that all these guys divide into? I think 24 would be the guy. Alright, so we've done step 1. We've just calculated the least common denominator of all the little denominators. And usually, I think this example is kind of extreme. Usually finding that common denominator is a lot easier. This one seemed more complicated for some reason, but it's usually fairly simple to calculate that LCD. Okay, now step 2. What does it say? What are we supposed to do with that LCD? It says you want to multiply the numerator and denominator of the complex rational expression by that LCD. Okay, is that all it says? Yeah, okay, so, and I think that's kind of confusing too, and it seems unnatural. But what they're saying is, I'm going to rewrite this guy just so I kind of have it written bigger. It's 1/2 plus 3/4, okay, that whole thing over 5/6 minus 3/8. So they're talking about the numerator of the complex fraction. That's this big part, 1/2 plus 3/4. That entire thing is the numerator, and the denominator is this entire thing, 5/6 minus 3/8. So really what they're saying is take 24, your LCD, and multiply it by that entire numerator, and multiply it by that entire denominator. So really, I mean, it's kind of confusing because you're using the LCD to do something. We'll see what it does later, but you're not really using it to get a common denominator. This LCD is going to get rid of all the little fractions. So it's like a tool. You usually use the LCD as a tool to get a common denominator, but we're actually using it to get rid of denominators. So that's the kind of confusing part. Yeah, that might, and I don't know since it's kind of confusing, that might help if you want to write it down, that's fine. But yeah, we are using the LCD of all the little fractions. That's the way I think of them. The little guys that are inside the big fraction. Of all little fractions basically to clear denominators. We're trying to get rid of all the little denominators. To clear all little denominators, not to get common denominators. We don't really care about common denominators. We don't have to deal with that kind of stuff. We're just going to get rid of all the denominators, so it doesn't matter anyway. Alright, and we'll see why it's true that it'll clear denominators. So let's see. Like we said, we're trying to multiply 24 by the numerator, but the numerator has two terms in it, so I'm going to have to distribute here. 24 times the 1/2, and then 24 times the 3/4. Same thing in the denominator. I'll do 24 times 5/6, and then 24 times 3/8. And it's complicated enough that I'd probably write that out. So I'm just going to write out 24 is multiplied by 1/2. I'll write those guys next to each other. 24 is multiplied by the 3/4. 24 is multiplied by the 5/6. 24 is multiplied by the 3/8. Let me fill those guys in there. So in the numerator, he was multiplied by 1/2 first. Oops, what the heck? Plus, and then he's multiplied by the second fraction, 3/4. And then that's over, oops, yeah. He's being multiplied by He's being multiplied by, in the denominator, 5/6. And then minus, now he's being multiplied by 3/8. So I just kind of bringing down all the fractions, like here, 1/2, move down here, multiplied by the 24, 3/4 here, the 5/6 down there, the 3/8 here. And now the next step is try to simplify each of these. And notice too that the 24, it's a whole number. So of course, if you're trying to multiply, for example, the 24 times the 1/2 here, you're going to have to put it over 1 and try to simplify. So really, all these 24s that I'm multiplying by, I'm going to have to put them over 1 to try and simplify them, so that I could maybe kind of cancel stuff or multiply across. Alright, so I'll focus on the top left fraction. So let me see about that guy. He is 24 times, or basically 24 over 1 times 1/2. That kind of reduces, right? 2 can go into 24 12 times. So really those two fractions multiplied together just becomes 12 over 1. Or just 12, actually. Because anything over 1 reduces to that number. So that became a nice whole number. And I think something similar is going to happen in the next fraction if I move to the right there. The second fraction, it's 24 over 1 times 3/4. The 4 can go into the 24 6 times. So really you're just left with 6 times 3, which is 18, over, I guess, 1 times 1, which is 1. But you don't have to write the 1 in the denominator if you don't want. Alright, then in the denominator, on the left side, we have 6 can go into 24 4 times. And what's left over is the 4 times the 5, that's 20 over 1. But that's going to become a whole number also. The very last fraction, the bottom right, 8 can go into 24 3 times. So you're left with 3 times 3, which is 9. And yeah, if you wanted to skip this step and you know anything over 1 is that thing, so why am I even writing the 1s? This really just comes down to 12 plus 18 in the numerator, since 12 over 1 is 12, 18 over 1 is 18. And then in the denominator, 20 minus 9, since either of those over 1 is just that thing. So it became really simple. We didn't really have to deal with adding or subtracting fractions. We just took the LCD, used it as a tool to get rid of all the denominators. And now that there are no denominators, it's just a matter of combining like terms and trying to reduce if we can. So we're left with 12 plus 18, that's 30, over 20 minus 9 is 11. I would try to reduce that if I could, but nothing divides into 11 and 30 at the same time, so that's kind of as good as that guy gets. So that's the idea. It seems, yeah, like I said, it's not really natural. You wouldn't maybe think to do it, but it works really well. It's really nice, as long as you remember how to do it. Let's practice it again on the part B here. So part B, first thing we're supposed to do is look at, like it says, all the little denominators. I have a t, I have a 5, and I have a t. And calculate the least common denominator of all those denominators. So like we've seen before, the least common denominator of rational expressions, you're going to want every factor you see. So I see a t, and then I also see a 5. He's in the second fraction's denominator. But either of them only occur once at most, right? Like the first fraction has t to the 1 power, the bottom one has t to the 1 power. So the highest power I see is a 1. Same thing with the 5. The highest power of 5 I see is a 1. So the LCD will be 5t. Now remember that. And then, okay, the next step is you're going to take the whole big numerator, this 1 over t minus 1 over 5, multiply it by that LCD, and then take the whole denominator and multiply it by the LCD. So I'm taking the least common denominator, 5t, multiplying it by the whole big numerator, and multiplying it by the whole big denominator. And then once we simplify it, it should work out really nicely. Alright, in the numerator I have two fractions, so I actually have to distribute this 5t. 5t times 1 over t, 5t times 1 over 5. So I'm going to write each of those guys, 1 over t, and then 1/5. I'm going to write the 5t next to each of those, so showing it's distributing. 5t times 1 over t, and then 5t times 1 over 5. Alright, in the big denominator, 5t, it's really only being multiplied by one term, even though t minus 5 looks like, I don't know, it looks complicated. It's only one fraction because it's t minus 5 over t. So really it's just 5t times that fraction, and we'll see what happens with that guy. 5 over t. Yeah, so we didn't have to distribute on the denominator. Excuse me. Okay. Now let's see if we can reduce this stuff. And if you do this right, you calculate the right LCD and you do all your math right, every single little denominator should cancel right now as I reduce. But before I reduce, I'm trying to multiply kind of like a whole number by a fraction. I better make all those little whole numbers, 5t, into fractions by putting them over 1. So I'm going to start with the top left fractions. If I reduce that, I notice the t's cancel. So all that's left really is 5 times 1 in the numerator, that's 5. And then 1 times 1 in the denominator is just a 1, so that's really it, 5. That whole first term looked complicated, but it just became a 5. And the second term, what happens with that guy? He's got the 5's cancel there on the top right. So who's left? Just minus t times 1. That's just minus t. There it is. Because you're just left with t times 1. In the denominator there, what are we left with? We got t. The t's cancel, right, on the diagonal. This t cancels with this t. So you're left with the 5 that was in the front times the t minus 5 that was on the second fraction, or the right fraction. Okay, and then this is where I'm supposed to see if I can reduce. So I would definitely not distribute that 5 into the t minus 5. Because remember, in order to reduce, you have to factor. So if I distribute that 5, it'd be kind of a waste of time. Because I'd probably have to refactor it again. You know, if you distribute the 5, it'd be 5t minus 25. But then I'd try to factor it, and factoring it would involve taking out that 5 that they had in common. So really, you don't want to multiply things out here. You want to leave everything in factored form. So now, this is where I want to see, can I factor anything? And then if I can I reduce anything? Are there any like factors here? Alright, well, I look at the numerator, it's 5 minus t. I'm going to try to put that in descending order of powers. It should be minus t plus 5. Because t has a 1 power, and the 5 is the constant, so it has a 0 power. And the denominator, thankfully, is already factored for me, so I don't really need to do anything there. But the numerator, the only thing I can really do to factor it, since they have nothing in common, is, remember we said that if the leading term is negative, you want to factor a negative out. So I'm going to try to do that and see if anything happens there. Alright, let's see. If I take a negative 1 out of the numerator, I say, okay, negative 1 times what is t? Negative 1 times what is negative t? That'd be t. And then negative 1 times what is positive 5? It'd be negative 5. So there's the numerator. And then I got lucky now because the denominator has that same factor, t minus 5. So I think I'm able to cancel the t minus 5s. And I almost feel like I must have done this problem wrong because this can't be right. It's too nice. All that's left is negative 1 over 5. And that's it. I don't think this problem can get any better than that. That's kind of as good as this one's going to get, I think. Alright, so I think this method's nicer. It seems, if you look at all the steps here, it looks like a lot of steps. But I think once you get better at it, you'll be able to skip some steps. You can, for example, at this stage up here, once you get really good, when I was trying to distribute the 5t, actually when I do these, usually what I think of is, I'll actually just start canceling right away. Like in my mind I'll go, this t cancels with this t, so it leaves the 5, and I'll just skip straight to this step way down here. And then, for example, if I try to think about distributing the 5t onto the 1/5, I notice that the 5's cancel, so the t would be left over, and that's where you get this t. So you're actually, once you get good at this, you're able to even skip that middle step. I wouldn't do it right away if this is new for you, but once you kind of get the hang of it, it's kind of nice. So I do think this seems like it's just as many steps as the previous method, but it really isn't. If you get really good at it, you can skip steps. Alright, let's try this last one, and then you should probably be able to tell which method you like better. And if you're still kind of on the fence, I'd say in the homework, try both. And that might help you kind of decide which one you like better. Alright, last one. Let's see. What are we supposed to do first? We're supposed to look at all the little denominators. Well, the numerator, or the big numerator, has only one denominator. It's little 3x, because this 1 is a whole number. He doesn't count. So 3x so far. The only other little denominator is the 9x, because this x here doesn't have a denominator. So really all you're looking for is what's the LCD between those guys, 3x and 9x. Well, I'm supposed to say the LCD, okay, I take any factor I see. Between those guys I see an x, but each of them only occurs once, so I only need one. And then you're supposed to take the least common multiple of their numerators, or sorry, of their coefficients. Between 3 and 9, the least common multiple is 9. So there's my LCD, 9x. Alright. In the next step, I'm supposed to multiply the big numerator by that thing, so 9x times this big boy, and then also the big denominator gets multiplied by it as well. And the numerator has two terms, so I'll be distributing the 9x onto either of them. Same thing with the denominator. It has 2 terms, so I'll be distributing the 9x onto both of them. And yeah, I think once you get good at this, you can probably just see what cancels as you go, but I'm just going to be really careful. I'm multiplying 9x first by the 1 in the numerator, times 1, okay, minus, and then the 9x times, this is the fraction that's in the numerator, it's 2 over 3x, and I'll see kind of what happens there. In the denominator I have 9x being multiplied first by the x that's in the front, so I got that first, times x, okay, and then minus the next fraction, 4 over 9x, that's also being multiplied by the 9x that I'm distributing onto it. Alright, I think it looks good. Now the first thing I notice is that the first term here, 9x times 1, I don't really need to worry about canceling denominators or reducing or anything. There's no fractions, so I really just go 9x times 1 is 9x. And that's it. So, but the second fraction in the numerator, 9x times 2 over 3x, it's a whole number kind of times a fraction, so I have to put that kind of whole number over 1 and then see what reduces. And I notice the x's cancel across the diagonal, but not only that, the 3 can go into the 9 3 times. So in the numerator you're just left with 3 times the 2 as your second term. 3 times 2 would be 6. And yeah, in the denominator you can think of there being a 1 left, but we know a denominator of 1 doesn't really do anything. It simplifies to a whole number. So the whole big numerator became 9x minus 6, which is really nice. Alright, now what? Let's see. The denominator, I have a 9x times x. There's no need to, make anything a fraction or anything. That's just a normal multiplying. 9x times x is 9x squared. Alright, but the second term I have there, it's 9x times a fraction, so I better put that 9x over 1. And notice everything cancels on that diagonal. 9's cancel outright, x's cancel outright. So that term, all you're really left with is the 4 that was there, minus 4. And the minus comes from just the subtraction sign that was in between them. Same thing in the numerator. So there it is. Now it's no longer a complex fraction or a complex rational expression. It's only complex if there are fractions within fractions, but we got rid of the fractions within fractions. So we're kind of done in a way, but remember, with all these problems in this chapter, you're always going to want to see if your answer reduces. We have to first factor if we can. And then if it factors, then we can see if it reduces. Are there any like factors? And if I look in the numerator, I notice 9x minus 6, they have a common factor of 3. I'm going to factor the 3 out there. If I factor 3 out, 3x minus 2 is left. Alright, in the denominator, 9x squared minus 4, that's actually a difference of squares, because 9x squared, that's something squared, 3x, and then the 4, that's something squared as well, 2. So that guy will be, okay, I think first, what can I square and get 9x squared? That would be 3x. That's what goes in the first spots. And then, what can you square and get 4? That'd be 2. Whew! And it does seem worth it now that I see what happens. We're going to reduce these guys. 3x minus 2's cancel. So in the numerator, you're left with the 3 that was in the front. In the denominator, you're left with the second factor at 3x plus 2. And that's it. And yeah, be careful. Don't be tempted to cancel those 3's, because the 3 in the denominator is part of that entire factor, 3x plus 2. It's a package deal. You can't cancel part of it. And there it is. Alright, so this section is pretty complicated, you know. And I don't know, I kind of hesitate to show two methods on how to do something, because I think it's just confusing, and then it's easy to mix them up. So like I said, I'd say try to kind of decide which one you like better. Try some problems in the homework one way, and then try some the other way. Decide which one you like better, and then I'd say just stick with it. Don't try to memorize both and use one time and use the other one some other time. I think it's just easy to get confused. I've graded exams on this stuff where people, they try to kind of mix the two methods together, and then they get lost because the two methods don't mix. You have to do one or the other, not both. So really, yeah, I'd say at a certain point you want to decide which one you like better and try to throw the other one out of your mind as much as you can. Alright, but thanks for listening, and hopefully it made some sort of sense. You got to be really careful with these problems. It's easy to make a silly mistake. But we're almost done with this chapter, so if you're kind of getting tired of this stuff, then don't worry, it's almost over. Also, if you like this stuff, then I'm sorry, it's almost over, because it's kind of sad, right? But I'll see you in the next video. Thanks for listening. Have a nice day.